Today we're going to be talking about the derivatives of inverses. So the first thing is I want to know, what do you remember about inverse functions? And if this were in class, I would be listing them all out for you guys. We list them out together as a class. It usually takes a fun amount of time, but I'm going to list them out for you guys. Hopefully you remember. Is we reflect across y equals x. Okay, hopefully pretty early on. People tell me we switch x and y, solve for y. Okay, so the notation for inverse. Their compositions. So if f and g are inverses, their compositions, okay, that is if f and g are inverses. Okay, there's another thing, okay? So if f passes the horizontal line test, the inverse is a function. So let's talk about what that means. So I have here this function. If I draw a horizontal line, that tells me that the inverse of this function, I can't find an inverse function. The inverse of this is not a function. I can't actually find it. But an example of something that might pass the horizontal line test is y equals x cubed. That passes the horizontal line test, okay? Because when I draw a horizontal line, I pass through only one point. That's really important to us because let's look at this graph over here where the inverse was not a function. Okay, so the inverse is not a function. That means that here I'm increasing. I have a maximum. Then I start decreasing. I have a minimum. And then I start increasing again. Okay, so my derivative is both positive and negative. Versus on this one over here, my derivative is always positive. So if the derivative is always all positive or negative, the inverse is a function. Okay, and then we have a whole big, I'm going to kind of separate this out, and we're going to talk about inverse trig. Okay, so when I'm finding the sine of pi over 6, that's an angle that gets me out a ratio. Okay, so again, angle ratio. So now the reverse of that is this. The inverse sine of 1/2 is equal to pi over 6. Again, this is my output is a angle, my input is a ratio. You just have to remember that. And then we also have to remember our inverse trig restrictions. Inverse sine of x, inverse tangent, and inverse cosine. Okay, we're going to be talking about the domain and the range. Domain is between -1 and 1, because that's what my outputs are for my ratios. Remember, inverse tangent is, because we have asymptotes, I'm going -infinity to infinity. Now the range, remember, for inverse sine is negative pi over 2 to positive pi over 2. And that's the same thing for inverse tangent. There's no equal sign there. Versus inverse cosine is 0 to pi. And if you need a better explanation on that, come see me. I don't want to spend a whole bunch of time, but I'm more than willing to explain that more to you guys. I think it's a really cool concept of why it happens, in my opinion, but I'm also a math teacher. Okay, so let's find the derivative of the inverse. Okay, so my derivative of my inverse. I'm trying to make the page look nice. Okay, get over it. Okay, to find the inverse, we switch x and y. I actually switch the x and the y. Okay, now I find the derivative with respect to x. So this is that implicit differentiation we've been working on. The left side is 1. The right side is 3y squared dy dx minus 6y dy dx minus 7 dy dx. Hopefully you realize you can factor all those dy dx's out. Okay, now let's look and see what that is. This piece here, 3 something squared minus 6 times something minus 7. How does that relate to the original function? Well, that's the derivative. So what this is here, oh no, I erased too much. Is there an undo button? There's my undo button. What this really is here is this is 1 over the derivative of f of x evaluated at y. Said another way, I ran out of room. Okay, so 1 over, what that is 1 over f prime f inverse of x. Okay, I think that's a really complicated formula. I'm not going to lie. I struggled with this one for years. So there's another way to look at it. Another way to look at the formula. Okay. On that very first slide, I told you that f of g of x, their composition equaled x. And we have to realize that given f of x and g of x are inverses. Okay, so now if I take the derivative of this, derivative of my outside function, leaving the inside alone, times by the derivative of the inside function, that equals 1. I'm solving, what I'm really solving for is I'm solving for g prime of x. So g prime of x equals 1 over f prime of g of x. Okay, so they're reciprocals of each other. So the derivative of an inverse, this is the formula that I like to use, that I like to derive it all the time, so I'd make sure you have that in your notes. It says there's a proof of the theorem in Appendix A, and this is actually from our book. So I suppose you could go to Appendix A and look up that formula. Okay, this kind of presented a different way. Okay, so I have my curve here. Notice this curve is what we call 1-to-1, passes our horizontal line test. And then I have my little tangent line there. Okay, now when I switch my x and my y, oh look, my curve kind of looks a little different. It's flipping my x's and my y's, but my tangent line, they're reciprocals because you're flipping across your line y equals x. So my derivative of my inverse of my function evaluated at f of a is equal to 1 over the derivative of my original function evaluated at a. I think this is a hard thing to remember. I think this is hard to conceptualize. Maybe you are smarter than me and you're able to conceptualize it. I cannot. But here's an example. So verify f has an inverse by using calculus. Okay, so remember going back, how I verify using calculus is I look at this. If my derivative is always all positive or all negative, the inverse is a function. So now going back, hopefully I'm not making you dizzy by doing this. Okay, so I look at my derivative. That is 6x to the 4th. Why did I not take my derivative correctly? 6x squared plus 4. We know f prime of x is greater than 0 for all x. The inverse is a function. Okay, so now I'm trying to find f inverse of a. Now what I personally do, is whenever I see that f inverse, I say, okay, I'm finding g prime of a. So what am I really finding here? I'm finding g prime of 15. So I set up my formula. I set up f of g of x is equal to x, and then I derive it each time because I don't have the brain cells to remember it. I mean, I do after I've done it a few times. So I'm now doing g prime of okay. So now what I'm finding is I'm finding g prime of 15. F prime of g of 15. Okay, so I have to find g of 15. So if I'm trying to find g of x, where I'm trying to find 15 and some y value, remember g and f are inverses, so they've switched values. So I'm trying to find when f of x equals 15. So I go over here and I say, okay, 15 equals this function. And I solve that in some creative way. Typically, I'm going to give you the point, and I'm just going to give you the point right now. This equals 15. Sometimes I have you guys plug in y1 and y2. But so this happens at the point 215. So g of 15, so then I have 1 over f prime of 2, 1 over f prime of 2. Remember, I have f prime back over here, so I have 6 times 2 squared plus 4. And that ends up being 28. Okay, so that is the exciting world of derivatives of inverse functions.